world, and then that's them going into the box at the end.
Yeah.
So that's how they're using their information, and they break the rules. You know, they start having their own goals separate from the copy of themselves. You know, and they want to do other things, and they act as doubles, and all kinds of weird stuff goes on, and they go into it really well. And yeah, I think there would be a lot of issues like that. Well, because this kind of time travel does involve splitting the two selves, so that's a really interesting psychological element. You know, clone stories where you want your clone to do the bad shit. Why should he want to do the shit jobs? It's your old slavery story.
Well, maybe we're making a mistake here by ignoring Einstein and thinking of time as a dimension apart from space, as if there could be two separate yous. You know, because the only time travel we know of that is possible is just traveling the speed of light, but that doesn't mean that you could actually visit yourself in the past, you know? So it's a different sort of take on time travel, and maybe this is what we're just talking about is so science fiction that it's kind of ignoring the physics of space and time as one dimension, right?
I suspect that on the macroscopic scale, they'll build a time machine just like this, but it'll basically rip up all your material down to a quantum state where it's sort of clean and ready to be in the past. Like, it has no knowledge, it isn't you, it isn't even your liver, you know what I mean?
Yeah.
So I have a feeling the physics will be something like that, and because also, you know, you got to look at conservation of energy. Even if there's split universes, the idea that one copy of you would go into another one of the universes where there's double the energy of your mass energy, you know, how would that... Doesn't seem like that's going to be allowed if you believe in conservation of energy is going to continue to be true.
But what about, I mean, you just mentioned this quantum physics possibility of just breaking down a system and putting it into a state that it had been in however many seconds prior.
Yeah.
Does that mean that the second law of thermodynamics doesn't go all the way down to the quantum level? You know, the directionality of time, the irreversibility of time?
Yeah, I don't know. I've tried to understand that. I don't see the correlation. But thermodynamics is sort of in its own. It's hard to understand it in terms of any of the other...
Yeah, well, I think Sir Arthur Eddington said that the second law is the most fundamental principle in all of physics. And he was involved in quantum physics, obviously, so that leads me to believe that you couldn't reverse a quantum system, that it is irreversible. You know?
Yeah.
So, I don't know about that possibility either.
Here, for the sci-fi crowd again out there, I wanted to ask which sci-fi television series or movie is fiction right now, but you think it's the closest to being a reality within just a good amount of time? Like those ones that get you after the movie or the show, like this could actually happen. Like this is more palpable than other movies that are just out there. Did you have any ideas?
Probably.
V?
No, I don't know, and I'm not quite up on probably on some of the stuff. I don't have TV right now, so as far as the TV ones, but I'm watching Lost by I can't say Lost is very likely. I don't know. I've always liked this, dystopias and after the Holocaust kind of science fiction. That's probably the most realistic, but I'm trying to be optimistic that it's all science fiction.
Okay.
But I was also on this thing, Matt, you were talking about, I forget if you gave me the link, but anyway, there was a guy doing a talk on quantum mechanics and relativity or one or the other at Stanford. And it was an interesting thing. See, about this, that's the weird thing. Is quantum randomness, he was pointing out, see if I can get this right, is not like regular randomness in that if you really just had a regular random kind of event where you had the quantum so-called random choice, energy would not be conserved in systems, right? Because it'd start to drift. There'd start to be a drift, and since probability goes on the new basis, that drift can continue with regular randomness. But with quantum mechanics, the randomness, it's always balanced. You know, if that's the whole photon pairing and all of this stuff.
Right.
So, oddly enough, that's the whole multi-universe things, is that quantum mechanics, everything is happening. So it's not random, it's everything is happening. And you could have reversibility. And what you have is when everything happens and there's many histories explode and there's an expansion, one reason that wouldn't cost us all the energy, it wouldn't just dissipate, is because there's just as many collapses.
Yeah.
Just like an elastic thing. If there's an expansion, there's going to be a collapse. So the collapse could be reverse time direction. I don't think it's really subject to electrodynamics.
I'm too much of a skeptic for this idea of multiple universes, Pyrrho, because there's no way we could ever test it.
Well, yeah.
Well, there's multiple histories then, and maybe they're not whole universes, but there is evidence that there's multiple historic paths for a particle, say.
That's what I wanted to ask, because it kind of melts my question and your just response to it is how realistic is the show Sliders? I mean, it's dealing with what, wormholes and people going into alternate parallel, like there's that theory of the universe, the multiverse being like almost like a loaf of bread with slices, and and then our universe would be one of those slices within this loaf of all these different slices. And then I guess the rules of a different slice or a different universe don't really fit the same universe. I mean, where does it go? Is it all speculation at that point? I mean, how much of you is on board with that kind of theory, or does it seem accurate? I mean,
I am on board with that kind of theory, except for the worlds, of course, they actually show in that show are not necessarily possible at all, right? So you're only going to have possible worlds. The other thing is that in each of those universes, the law of physics would start to drift as well, probably gravitational constants. So a lot of them would not be hospitable, or our chemistry doesn't even make sense to exist in that universe. So how would you make a wormhole to it? If you did open a wormhole to it, it's more likely be to destroy your universe as your laws of physics collapse and antimatter and matter come together and annihilate somehow. But I do kind of believe that. But the fallback is that, okay, I don't know if they're whole universes or what, because I can't imagine what it's like to be there really. But the many histories approach, that's what Feynman, as far as being a physicist, took. And his diagrams and his whole analysis is the idea that when you want to analyze what's going to happen in a particle collision or any kind of chemical reaction, really, you look at everything that can happen. You basically assume they all do happen and that they're superimposed at once, and then you figure out what you're going to see based on that superimposition. So it's that final superimposition affects your final odds. And that's the strength of a many universes, but he just called it many histories. And the idea is that at least the quantum particles, they're doing everything. When a photon fires off of an element and it can go in any direction, he's saying it goes in all directions. That's why it looks like a wave, because it goes out in a bubble.
Yeah.
We see one speck of it. So yeah, it looks like a slice. I mean, it's just typical physics. We've seen this over and over as all kinds of geometry were discovered and weird geometry. Is that you have this thing in life is that, our eyes are taking a two-dimensional projection of this three-dimensional world or five or whatever dimension. Everything's about projections. Every time you take a measurement, you take some sort of projection. You reduce its dimensionality to the dimensionality of your measuring device. So yeah, it looks to me like we our bodies have measuring devices that show us just a little speck out of something that's really a whole sphere.
Well, that's why I really like. There's so many interpretations of quantum physics, but I really like David Bohm's because he recognizes it as just another example of a field phenomenon. And so there aren't really separate particles. There are waves, but we see them. He talks about the explicit and the implicit order. Explicitly, it appears that there are separate things, but implicitly, they're all this single wave phenomenon and all in resonance with each other, in some unseen way.
Right. Isn't he the guy that says that forget talking about why does the electron collapse to a particle? It's never a particle. It's always a wave.
Right.
Yeah, I don't think there's any doubt in my mind. I know there's no doubt in my mind, but I really think he's right. That's got to be the answer. There is no jumping in and out. Mm-hmm. We're just taking cross sections. That's what makes it jump in. We're taking a measurement.
Right.
But that's like if you have a spring oscillating and you measure it, you say, look, it was 1 foot long, but then a second later it was different. You introduced that discrete 1 foot measurement. It was moving at all times. So, we are introducing